Hello everyone, welcome to my channel. So I've started offering specialized one-on-one classes in physics, chemistry and math EE for both SL and HL. So for the rates, the standard rate is $35 per hour. If you book like 5 or more classes, it'll be 30, and if you book 10 or more, it'll be 25. So these courses will be tailored to your needs. Whatever you want to learn, we can discuss in these classes. Please don't hesitate to reach out to me. You can contact me at this given email, and yeah, to schedule your class. So with this, let's get started with this paper. Thank you. Hello everyone, welcome back to my channel. So today we'll be discussing paper 3 of AA Math HL of the November 2024 attempt. So let's start with the first question. So trout is a type of fish. At the start of the year, a lake is estimated to contain 6,000 trout. So at the first year, you have 6,000 of these fishes. Estimates that the number of trout will increase 10% per year. At the end of each year, the year owner proposes to remove 500 trout from the left to prevent overpopulation. Fine. Therefore, relationship between Tn and the predicted number of trout at n years and Tn plus 1. So this is the predicted formula. So this is fine because every year it's increasing by 10%. So 1.1 of Tn, and also you're removing 500. Get this expression, and T1 is given as 6,000. So first you have to use you have to use the formula to verify that T2 equals 6100. So for the first one, we will use this formula. So we'll get T2 if I put Tn as 1, right? If you put n as 1, so it will be 1.1 T1 minus 500. Yeah. Now here I know T1 is 6,000, so I'll just place 6,000 in this equation. Yeah. So 1.1 times 6,000, this is 6,600. 6,600 minus 500. So finally we get we'll get T2 as 6,100. This is exactly the value which we had to prove. Now, so we'll do B1 now. So we have to verify that T3 is 6210. So for T3, I can use the same equation. So T3 will get T3 if I put n equals 2. So T3 would be equal to 1.1 T2 minus 500. So 1.1 times 6100 minus 500. This will be T3. So upon simplification, I'll get T3 as 6210. And this is what I had to prove. Okay. And similarly, we have to find T4. So T4 would be, basically if I put n equals 3 in this equation, I'll get T4. So which is 1.1 T3 minus 500. This will be 1.1 times 6210 minus 500. Now if I put it in a calculator, I'll get 6331, which is your T4. So with this, the first three parts are done. We have verified that T2 is 6100. We have verified that T3 is 6210, and finally we have found out the value of T4, which is 6331. Okay. Now moving on to the next part. It is also known that Tn is equal to 6,000 1.1 to the power n minus 1 minus 500 times 1.1 to the power n minus 1 divided by 1.1 minus 1. So we have to show that Tn is equal to this. Okay, so basically we have to simplify this formula. That's it. So for the simplification, 6,000 1.1 to the power of n minus 1. If I open the brackets, it is okay, I can keep it like this. 1.1 to the power of n minus 1 minus 1. Denominator is 0.1. So 500 divided by 0.1 is 5,000. So writing it accordingly. For n minus 1 minus 1. Now I'll just open the bracket and simplify. So I'll get 6,000 1.1 to the power n minus 1 minus 5,000. 1.1 to the power of n minus 1 minus is plus, so plus 5,000. 6,000 minus 5,000 is 1,000. So 1,000 1.1 to the power n minus 1 plus 5,000. This would be your Tn, and this is what we have to prove. It exactly matches with this expression. So now we have to use this equation to find the value of T6. Okay, T6 will be, I'll just replace n with 6 on the right side. So 1,000 1.1 to the power of 6 minus 1 plus 5,000. Yeah. So if I plug it in your calculator, 1.1 to the power of 5 times 1,000 plus 5,000, this will give me approximately 6610.51. So number of trouts cannot be a fraction, so we will round it down to 6610. Okay, so this is the number of trouts after 6 years. Now moving on to the next part. After deciding that the trout population will increase too quickly, the lake owner proposes instead to remove 750 trout at the end of every year. So okay, so they have given you the predicted relationship, so starting as 6000. And also they have given you the other formula. So dn is minus 1500 1.1 to the power n minus 1 plus 7500. So d1 is we have to show that dn plus 1 minus dn, it is minus 150 1.1 to the power of n minus 1. Okay, so yeah, so I can use this equation first. So dn plus 1, if I subtract dn from both sides, I'll get this expression. I'm just doing minus dn on this equation, right? So my left side is sorted. The right side would be 0.1 dn minus 750. And for dn, I can use this equation. I can just substitute this equation instead of dn. Minus 1500 plus 7500 minus 750. Now if I open the brackets, what I'll get is minus 150 1.1 to the power of n minus 1 plus 750 minus 750. Now these two will get cancelled out. So finally I'll get d of n plus 1 minus dn. This is equal to minus 150 1.1 to the power of n minus 1. This is exactly what we need to show here. So okay. Now for the next part, you have to use the result in D2 to deduce that predicted number of trout at the start of any year will be greater than the predicted number at the start of next year. So basically the number of trouts is decreasing. That's what we need to show here. Right. This can be done pretty easily. So this is D1. We'll do D2 now. So dn plus 1 minus dn, this is equal to minus 150 1.1 to the power of n minus 1. Right. Now for any value of n, 1.1 to the power of n minus 1 will always, so in just write like this, will always be greater than 0. So whatever value you can put on n, 1.1 to the power of n minus 1, this quantity, right, this quantity will always be positive. Right? So therefore, minus 150 1.1 to the power n minus 1, this will always be negative. Yeah. And therefore, dn plus 1 minus dn, this will always be less than 0. So if I shift dn to the other side, so dn plus 1 is less than dn. That's what we need to show. That predicted number of trout at the start of any year is greater than the predicted number of start of the next year. Okay. So dn, our current year, the number of trouts in our current year is greater than the number of trouts which we'll be starting with in the next year. Then the second part is okay. Now the third part. Determine the first year in which there will be no trout remaining in this lake. Okay, so we can just use this equation and we can just equate it to 0 and find n. Okay, for part E, we can put dn equals 0. So minus 1500 1.1 to the power of n minus 1 plus 7500, this will be equal to 0. So yeah, so from here, if I try to simplify, this is equal to minus 7500 by minus 1500. Fine. So the right side becomes 5 and this is 1.1 to the power of n minus 1. Now if I take ln on both sides, 1.1 to the power of n minus 1, this is equal to 5. N minus 1, okay, this is equal to ln 5, sorry. Yeah, n minus 1 times ln 1.1 is ln 5. From here, n minus 1 is ln 5 by ln 1.1. ln 5 divided by ln 1.1, this gives you 16.89. So n minus 1 is 16.89. Okay, from here I can write n equals 16.89 plus 1, which is 17.89. Fine. So the answer would go like this. After after 18 years, yeah, the question was yeah, there will be no trout remaining in the lake. Done. That's our part E. Now moving on to part F. The lake owner now considers a more general approach where D trout is removed at the end of each year. So they have given you the formula. So Cn is the predicted number of trout in the lake. Find the value of D such that the predicted number of trout at the start of each year is constant. Okay, this is interesting. If the number of trouts at each year has to be constant, basically your Cn term should be independent of n. So the nth term basically should cancel out. So Cn would be 6000, 1.1 to the power of n minus 1 minus 10d, 1.1 to the power n minus 1 minus 1. Yeah, I'll just open the bracket on the left side. Minus 10d, 1.1 to the power of n minus 1 plus 10d. I can just take 1.1 to the power of n minus 1 common from these two terms, which will be 6000 minus 10d. 10d. This is your Cn. Now, this term has to be 0, and this term can only become 0 if 6000 minus 10d equals 0. 6000 minus 10d equals 0. 10d equals 6000. So dividing both sides with 10, I'll get d as 600. If he removes 600 fishes every year, the predicted number of trout at the start of each year would be constant. So 600 fishes have to be removed. Now the next part. So okay, the model predicted the trout has been generated using sequences. So this is the sequence, okay, and you have to use mathematical induction to prove this. Prove that un is equal to u1 to the power of u1 times r to the power n minus 1 minus d times r to the power n minus 1 divided by r minus 1. Okay, fine. So for mathematical induction, there are 3 steps. First, we have to show that this relationship is true for n equals 1. Then we have to show, then we have to assume that this relation is true for some value n equals k, and then we have to show that this function is true. I mean, yeah, it is true for n equals k plus 1. So 3 steps. Let's do one by one. Okay. So the first step, for n equals 1, the left hand side of this equation is just u1. Okay. Left hand side will be equal to u1. And what happens to the right hand side? Right hand side is u1 r to the power of 1 minus 1 minus d times 1 minus 1 divided by r minus 1. So u1 r to the power 0 is u1, and this is d to the power r to the power 0 is also 1 minus 1 divided by r minus 1. So this thing becomes 0, this side. This 1 minus 1 is 0. So RHS is also u1. Now, as the left hand side is equal to the right hand side, fine, the formula holds true for n equals 1. Now, so first part is done. Next part is we have to assume it's true for n equals k. So, n equals k, right? Now we'll write the formula. So uk plus 1 equals sorry, uk would be equal to so this is the formula. Uk equals u1 r to the power of k minus 1 minus d times r to the power k minus 1 divided by r minus 1. This is our uk, right? I know this is true. We can use this result in our the next step. Now for the last one, for n equals k plus 1, you have to do this. It's a little bit tricky here. So we have this expression here. If I put n equals k, I'll get an expression for k, uk plus 1. So uk plus 1, if I put it as n, is r uk minus d. See, yeah, fine. So this is the expression which we got from here. Now here, what I'll do is I'll substitute the value of uk. So we'll substitute this value in this expression. Let me add a page here. So yeah, uk plus 1 is equal to r times u1 r k minus 1 minus d times r k minus 1 divided by r minus 1 minus d. Yeah. Now we will open the bracket and try to simplify this. So u1 r to the power k minus 1 times r is r to the power of k minus d times, if dr r to the power of k minus 1 divided by r minus 1. I have to include this d, so I'm just multiplying and dividing with r minus 1. Next, if I open the brackets, I'll get d r to the power k minus r divided by, and I can combine them together, minus d times r minus 1. So u1 r to the power k, I can take negative d common. It will be r to the power k minus r plus r minus 1 divided by r minus 1. So if you simplify this, this cancels out. So u1 r to the power k minus d r to the power k minus 1 divided by r minus 1. This is u. Yeah. This is exactly u k plus 1. And this is the expression we need. Okay. In this equation, if you place u as k plus 1, so guess what? This power will become k plus 1 minus 1. This is k. So this is k. So u1k minus d r to the power k minus 1 divided by r minus 1. u1 r to the power k minus d r to the power d times r to the power k minus 1 divided by r minus 1. So we can say, hence by the principle of mathematical induction, mathematical induction, the formula holds true for all n. For all values of n. That's it with question 1. And now we'll start with question 2. Starting with the next question, we have a polynomial which is said to be palindromic if the sequence of its coefficients remain the same in reverse. The question asks you to investigate some properties and solutions of palindromic polynomial equations. Okay, so palindromic polynomial equations will be in this form: ax squared plus bx plus a. So, you know, the order remains the same. If you move from left to right, it's aba. If you move from right to left, it's still aba, right? So here these are some palindromic equations they have given. Now, so this is the first question. So they have given us a quadratic equation which has roots 2 comma 1 by 2. These roots form a reciprocal pair since one root is reciprocal of the other. There's another way of checking reciprocal roots, that is the product of these two roots should be equal to 1. Fine. So first we have to determine the roots of x squared plus 4x plus 1. So let's start this. Okay, so we have to use this s plus minus root t form, so we have to use the quadratic formula. So for the first one, I'll first find the discriminant. Discriminant is b squared minus 4ac. Yeah. So 4 squared minus 4, a is 1, c is 1. Right? Which is 16 minus 4 giving us 12. Right? And root x1 will be minus b plus root d by 2a. The other root would be minus b minus root d by 2a. Okay, so minus b, so b is 4, so minus 4 plus root 12 divided by 2. This is the first root, and the other root would be minus 4 minus root 12 by 2. Now, root 12 can be root 12, like 12 can be written as 4 times 3. I can take the 4 out of the root, which is 2 root 3, right? So 12 can be written as 2 root 3. Minus 4 minus 2 root 3 divided by 2. If I simplify from here, it will be minus 2 plus root 3. This is the first root. Second root would be minus 2 minus root 3. Fine. So the roots would be, roots of this polynomial, this would be minus 2 plus minus root 3, which is exactly in the form s plus minus root t. Now, we have to now show that these roots form a reciprocal pair. So for reciprocal pair, I can just, just multiply them together and check whether the product is 1 or not. So minus 2 plus root 3 times 2 plus 2 minus minus 2 minus root 3. So it is a minus b, a minus b times a plus b, right? So I can write it as a squared minus b squared minus 2 whole squared minus root 3 squared. Okay, minus 2 whole squared is 4, root 3 squared is 3. So 4 minus 3 is 1. Therefore, minus 2 plus root 3 and minus 2 minus root 3 are a reciprocal pair. So that's all about question A. We'll now move on to question B. We have to find the complex roots of x squared plus, we have to show that complex roots of x squared plus 1 form a reciprocal pair. Okay, so for part B, x squared plus 1 equals 0, which is x squared equals minus 1. So x would be equal to plus minus root of negative 1. And I'll get x as plus minus root negative 1 is I. So the first root is I, second root is minus I. Okay. If I multiply the roots together, x1 times x2, this will be I times negative I, which is minus I squared. I squared is equal to minus 1, so minus times minus 1, which is equal to 1. Therefore, roots form a reciprocal pair. Yeah. Now it's given that px is equal to ax squared plus bx plus a. We have to verify that px is equal to x squared times p of 1 over x. Okay. So for part C, we have to first find p of 1 over x. Yeah, add another p here. Yeah. So p of x, this is equal to ax squared plus bx plus a. Now, p of 1 over x, this will be equal to a of 1 by x whole squared, b times 1 by x plus a, which is a by x squared plus b by x plus c. Now, x squared p of 1 by x, this will be equal to x squared times this equation. So x squared times ax squared will give you a, bx times x squared is bx, and yeah, b over x times x squared is bx, and not c, this is a, and a times x squared, and this will also be a, sorry, yeah, a times x squared is plus ax squared. So this can be rearranged, and we can write as ax squared plus bx plus a. Now, this and this are exactly the same, so we can say that px is equal to x squared p of 1 by x, right? So hence proven. So that's all about part C. We had to prove px is x squared times p of 1 over x, and we have successfully proved that. Yeah. Now part D and D. You may assume that result of the polynomial px of degree n is palindromic only if p of x is x to the power n times p of 1 by x. Use px equals x to the power n p of 1 by x to show that if alpha equals 0 is a root of px, then 1 by alpha is also a root. Okay, fine. So for part D, yeah, if alpha is a root px, then guess what? I can write it like this: p of alpha equals 0. Yeah. And if I put alpha in this equation, what will I get? So p of alpha would be equal to alpha to the power n p of 1 by alpha. Now our p of alpha is 0, so I can write alpha to the power n p of 1 by alpha, this is equal to 0. Now alpha is not equal to 0, so I can divide both equations with alpha to the power n, so which will give me p of 1 by alpha as 0, or 0 by alpha to the power n, which is 0 basically. So p of 1 by alpha is equal to 0. This is possible when 1 by alpha is a root of px, so therefore 1 by alpha is also a root of px. That's our part D. Now moving on to part E. Fx is px times qx, where p and q are palindromic polynomials of degree n and m respectively. Okay, show that f is a palindromic polynomial. Okay, fine. So for part E, px would be, px has a power order, px is n and q is m. So this will be x to the power n p of 1 by x. Q of x would be x to the power m q of 1 by x. Okay. Now I know fx equals px times qx. So from here I can write f of 1 by x. This is equal to p of 1 by x times q of 1 by x. Now, okay, so we have to show that fx is a palindromic sequence. So fx is px times qx. We'll input the values of p and q from here, right? So x to the power n p of 1 by x, x to the power m q of 1 by x. X to the power n and x to the power m can be combined together to write x to the power n plus m, which is times p of 1 by x times q of 1 by x. P of 1 by x times q of 1 by x is f of 1 by x. So fx is basically x to the power n plus m f of 1 by x. Now this is exactly the definition of a palindromic sequence. right? So instead of this, just write f and x to the power m plus n, let's say, is another like integer, let's say p or q, so x to the power p, right? So exactly whatever we have got for fx, that is the definition of a palindromic sequence, right? Which is exactly of a palindromic sequence, and therefore fx is a palindromic polynomial. Okay, now we have these two parts. Let's start. So fx is fx is given x to the power 4 plus 2x cubed minus x squared plus 2x plus 1. This polynomial can be expressed in the form x squared plus ux plus 1, x squared plus vx for 1. We have to find the values of u and v. Okay, so basically I will expand the left side and compare the coefficients on both sides, right, for part f. 2x plus 1, this is equal to x squared plus ux plus 1 times x squared plus vx plus 1. I'll keep simplifying the right side. So x to the power of 4 plus vx cubed plus x squared plus ux cubed uvx squared ux x squared vx and 1. Now if I take things common, from x cubed I can take u, and so like if I take x cubed common, it will be u plus v. From x squared term we have these 4. So x squared term is we have x squared, so it's uv plus 2 for x squared. For x it's again u plus v, just u plus vx, and finally we have 1. So this is exactly equal to this. If these two has to be equal, the coefficients of x squared would be the x cube would be the same, the coefficients of x squared would be the same, and coefficient of x would be the same. So from this I can write 3 equations. First is u plus v should be equal to 2. This will be my first equation. Then uv plus 2 equals negative 1. And from the third equation, again we are getting u plus v equals 2, which is not needed because I have considered this equation here. So just I will not consider it in my solution because you have the same equation. Now we'll solve these two equations, u plus v equals 2 and uv plus 2 equals 1, to solve for the values of u and v. So first I'll start with this equation. uv would be equal to negative 3 and v is equal to negative 3 over u. Now I'll plug in the value here, u minus 3 over u equals 2. So u squared minus 3 equals 2u, multiply both sides with u, and then u squared minus 2u minus 3 equals 0. And factorize it easily, which is u squared minus 3u plus u minus 3 equals 0. Okay, so this will make this u minus 3 times u plus 1. So from here you can have two values. First is, right in the next page, u minus 3 equals 0 or u plus 1 equals 0. So either u is 3 or either u is equal to negative 1. If u is 3, v would be equal to negative 3 over 3. So v is negative 1. And if u is 1, v would be basically negative 3 by negative 1. So v is equal to 3. So either v equals, so u3 v minus 1 or u1 v3. Okay. Now in this question, they have given us a condition that u will be less than v. Right. If I check here, in the first case, u is 3, v is negative 1. So u is bigger than v. So this is rejected. And this is accepted as u is smaller than v. Okay. So therefore, u equals negative 1 and v equals 3 is the only solution. Right. Now we'll move on to the last part of this question. Using this, we have to find the exact complex and purely real roots of this equation. Okay. We have part h here, no problem. Okay. So from this equation, okay, ux. So this is my equation now. This is your fx, x squared plus 3x plus 1 equals 0. So from here I can get two equations. And x squared plus 3x plus 1 equals 0. Fine. Now I'll use the quadratic formula to find the roots. One plus minus negative root 3 by 2. So here x can be written as 1 plus minus I root 3 over 2. So two solutions from the first, like from this equation, x1 which is I plus 1 plus I root 3 over 2 and 1 minus I root 3 over 2. Okay. Other two solutions I'll get from here, where x is equal to negative 3 minus b plus minus root under b square minus 4ac. 4, a is 1, c is 1, 2. So x is minus 3 plus minus, so it's 9 minus 5 which is 5, 9 minus 4 which is 5. So x is, so x3 would be minus 3 plus root 5 by 2, okay, and x4 would be minus 3 minus root 5 over 2. So for this question, roots of fx will provide the list 1 plus I root 3 over 2, 1 minus I root 3 over 2, minus 3 plus root 5 over 2, minus 3 minus root 5 over 2. Yeah. So that's the answer to question G. Now we'll move on to the last part, which is part F. So we have this palindromic polynomial equation where n is odd. Show that minus 1 is always a root of this equation. Okay. So px is equal to, px is this equation, right? So if I want to find p of negative 1, it's negative 1 to the power of n, a1 minus 1 to the power of n minus 1, a2 minus 1 to the power of n minus 2. Then at the end, a2 times minus 1 squared plus a1 times minus 1 plus 1. Okay, this is p of minus 1. Now, if n is odd, then minus 1 to the power n, this will be what? This will be minus 1. Minus 1 to the power n minus 1. This will become an even number. Minus 1 to the power n even number is a plus 1. Yeah. Minus 1 n minus 2. Again an odd number at the power. So minus 1. So it is alternating negative numbers. Okay. So one positive, one negative, like this. C is will go. So basically, if I plug in p of negative 1, I just simplify this. So minus 1 plus a1 minus a2 plus a3. Okay. Then at the end, you'll have minus a3 plus a2 minus a1 plus 1. If you check here, all the terms basically cancel out. Minus 1 plus 1 cancels out. Plus a1 minus a2 plus a2, a3. So p of negative 1 becomes 0. Okay. Therefore, negative 1 is always root of a palindromic polynomial if n is odd. Done. With this, we are done with paper 3, and I'll post the solutions of paper 1 and paper 2 shortly. Till then, thank you for watching till the end of the video, and see you in the next one. Bye bye.